or something.
Plus or minus 30.
There we go.
To survey critical areas of the Arctic seafloor. Data collection from Project Cornerstone will be combined with bathymetric measurements from previous surveys to support a submission under Article 76 of the United Nations Convention on the Law of the Sea, UNCLOS. Information on the limits of the continental shelf beyond 200 nautical miles from the baselines from which the breadth of the territorial sea is measured shall be submitted by the coastal state to the Commission on the Limits of the Continental Shelf. Defence R&D Canada was tasked with providing 2 long-endurance AUVs, designed and built by International Submarine Engineering to specifications required to conduct survey missions in the Arctic Ocean. The Polar Continental Shelf Program's base, located at Resolute Bay on Cornwallis Island, bordering Barrow Strait and the Northwest Passage, serves as the main staging area for Project Cornerstone. The final ice hole dimensions are 6 feet wide and 28 feet in length. The AUV communications team sets out to deploy an underwater acoustic modem field and a terrestrial networked radio system to establish communications with the AUV. 6 more, considerably smaller ice holes are drilled circling the AUV ice hole with a 1 kilometer radius. The generator powers an 8-inch ice auger to create a 10-foot vertical hole through the ice into the sea below. A modem is deployed and a GPS location is recorded. A networked radio system can activate and monitor any one of the 6 modems. The rear load hatch of the DHC-5 Buffalo opens, containing one entire AUV, boxed in sections, with consoles and recharging equipment. The modular design of the AUV allows for many shipment configurations. Sections are transferred from the runway to the camp in order of assembly. Are loaded on the track and wheeled into the AUV tent. The adjustable track system allows for free-rolling sections, a flexibility required to install components, make all necessary connections, and properly align sections. Connections are made between the main computer and inertial navigation system. One of the 2 battery trays is loaded. These dry components are housed in the watertight sections of the Explorer. When the control surfaces and nose cone are installed, all sections are sealed together and secured. An assembled Explorer rolls into the deployment tent, stopping under the gantry. The AUV team secures the Explorer to the lifts, removes the section dollies, and deploys the vehicle. The Explorer is lowered 30 meters into a dark Arctic Ocean. With lines released, the prop begins to turn and Explorer powers off out of sight, beginning its first mission. Through the modem field, the short-range localization system utilizes acoustic packet travel times to determine the vehicle's location and monitor its position during the lengthy spiral descent to the deep ocean bottom. Explorer's inertial navigation system begins to gather and process positioning and navigational information. With a fixed starting position and a pre-programmed mission, Explorer begins the journey. The Doppler velocity log begins bouncing sound pulses off the seafloor. The shift in frequency of the return sound determines the AUV's velocity. Information gathered from the Doppler log, depth sensor, and other onboard sensors is fed into the inertial navigation system, which in turn makes adjustments as needed to guide the AUV to its projected target. Explorer autonomously detects obstacles and avoids them as it makes its way through Wilkins Strait between Borden and Brock Islands, out into the Arctic Ocean. 9 hours into an estimated 60-hour journey, the main and remote camps receive information that the AUV has successfully passed a checkpoint and is making its way to the drifting remote camp. An ROV, a small remotely operated vehicle, is deployed to scan the ice under the camp, and once Explorer is located, recovery lines are attached to the AUV and the vehicle is returned to just under the ice hold, winched up into the catchy device and secured. In what is considered a groundbreaking initiative, Explorer receives an underwater charge, while significant stored data is downloaded from its computer. Once fully charged, a new mission is programmed and Explorer is deployed from the remote camp. After a long spiral descent, the AUV maintains a holding pattern near the bottom. It is given the go command along with a sequence of prompts to ensure the sounder is operating and collecting data. With two-way communications, the AUV team is able to monitor the telemetry which indicates the vehicle is on a near-perfect heading and is safely proceeding on its mission. Explorer is now gathering data beyond Canada's 200 nautical mile coastline. The sounder collects bathymetric data in the uncharted area known as Severus Spur. 2.5 days after deployment, with the mission completed, Explorer homes in on the remote camp's beacon and finds its way to rest under the ice, less than 30 meters from the ice hold. Bathymetry is downloaded, batteries are charged, and Explorer descends one last time for the journey to the main camp.
By the end of the operation, the AUV, which is now officially christened Euphoria, successfully collected over 1,000 kilometers of bathymetric data in a continuous 10-day mission. It successfully homed to the remote ice camp from a distance of over 50 kilometers during the transit out, and again at the end of the survey mission. Euphoria also traveled to water depths of greater than 3 kilometers during these missions. Individually, these accomplishments are remarkable. Collectively, they represent a world record for under-ice operations in the Arctic and have provided critical data for Canada's UNCLOS submission.
L'Ictineu 3 és un projecte molt ambiciós que permetrà als científics catalans baixar fins a profunditats de 1.200 metres de profunditat i convertirà Catalunya en la 6ª potència del món amb capacitat de baixar més profunditat. I amb això podrem explorar grans quantitats de coses que fins ara era impossible explorar.
Significarà tenir una infraestructura d'estat molt potent per respondre tant a necessitats del país en quant a recerca científica i recuperació del patrimoni aquàtic, com també per poder respondre a emergències en cas de necessitat i en general per poder gestionar el medi marítim com fan tots els països avançats.
És innovador perquè ens el vam plantejar partint de zero, que no en sabíem de tecnologia de submarins, i vam anar a fer, doncs anem a fer el millor submarí del món, i vam estar innovant amb totes les parts que havíem vist que en el món de la tecnologia submarina no estaven prou desenvolupades, i nosaltres n'hem anat doncs, amb les bateries, amb el material del casc, que reduïa el pes, amb un munt de coses diferents, i sense tenir unes idees preconcebudes de com havien de ser els submarins. Això, junt amb el talent de l'enginyeria catalana, ha fet un submarí que està sent molt reconegut a nivell internacional. Després de més de 2,5 milions d'euros invertits i gairebé 9 anys, ara és el moment de posar el submarí a l'aigua. D'aquí poques setmanes aquest submarí pot estar a l'aigua si vosaltres ens ajudeu a acabar-lo i participeu a la campanya de subscripció popular.
Us demano que col·laboreu perquè d'aquí ben poc l'Ictineu 3 comenci a explorar el nostre Mediterrani i perquè les més de 700 persones i institucions que hi han treballat i hi han dedicat esforços vegin el seu somni fet realitat. Si no aconseguim tots els diners que falten, perdrem una oportunitat única d'exploració i coneixement. Aquest submarí s'ha fet en matèria gris 100% catalana. Això no ho podem deixar perdre. Ajuda'ns, volem veure el teu nom escrit al submarí.
Ara és l'hora de la veritat. Fem l'esforç final. Posem a l'aigua l'Ictineu 3. Ajuda'ns a aconseguir els 60.000 euros que ens manquen per fer realitat el submarí científic català.
My name is Gretchen Schmoder. I am a geophysicist and the marketing director for Geometrics. The G882 is a total field magnetometer built for all purposes. It's a smaller instrument that's easily handled by one person. It can be put on the back of pretty much any sized boat. One of the nice features of the G882 is that multiple units can be deployed at once. Someone can deploy up to 4 magnetometers in the water for wide swaths of data collection that will reduce your time in the boat and ultimately reduces your cost. The G882 has a 10 to 20 hertz sample rate, high sensitivity and low noise. And the benefit of that is that you're able to detect small objects at a larger range. One of our interesting research projects was to take a transverse gradiometer, or TVG, array of G882 magnetometers to Pearl Harbor. The idea for this study was to identify the difference between debris field debris and the UXO that may also be present in the debris field. After deployment, we brought the data home and using sophisticated techniques, we're able to differentiate the noise from the debris field from the actual target, or UXO. The final results of this survey really highlighted the ability of the G882 to map and characterize UXO. During wind farm construction, the possibility of UXO exists, which can create quite a hazard for those who are doing the installation or even after the installation is complete. UXO is a safety hazard, particularly in places that were heavily bombed during World War II or other conflicts. Right now, with the wind farm construction happening in the North Sea, there are hundreds of magnetometers searching for any leftover UXO. The G882 is a standard magnetometer used for UXO surveys in the North Sea.